All right, in the next section, let's talk a little bit more about how we can visualize features and maybe even entire classes with backpropagation. So the next idea we're going to discuss is beyond just trying to visualize the gradient, the derivatives, what if we try to optimize the image entirely from scratch to maximally activate a particular unit? So before we were trying to find image patches that activate a unit and then figure out which pixels in those patches actually are responsible for the activation. Now we're going to try to actually generate the entire patch, or maybe even the entire image, entirely from the network. So before, we just wanted to compute which pixel influences a particular unit for a given image. Now, what we're going to do is we're going to calculate the derivative of a particular unit with respect to an image, and then we'll actually modify the image to activate that unit even more. And this is very nice because we don't actually need any particular image to start with. We could just generate a completely random image, just like random noise, and then iteratively modify it in this way to optimize it so that it maximally activates a particular unit. And this might be preferable because it provides, in some sense, a more unbiased look into what a unit is doing. It's not about finding an existing image that activates a unit, it's about actually generating an entirely new one. Now, unfortunately, if we just use this procedure naively, it likely won't work very well. Okay, so what optimization problem is this solving? Well, this is trying to find the x that is the argmax of the activation, and the activation is a function of x, so we can write ALMNP as a function of x. More generally, we could imagine this as finding an x that maximizes some objective s of x, where s of x could refer to any combination of units or class labels. Like, for example, we might want to maximize the activation of a particular filter at all positions in the image. Or we might want to maximize the probability of a particular class to try to find what is the network considered to be the prototypical image of that class. All right, so the reason this by itself doesn't work very well is that it's a little too easy to produce really crazy images if you just do this naively. So think back to this picture of the derivative of the cat neuron. If we want to optimize an image that fires this unit more, well, you can see that this unit has a positive derivative as we make the eyes of the cat more blue. So what if we set the blue channel to like 1 billion or something? That will very, very strongly activate that unit. It'll kind of create like a super cat with gigantic, infinitely bright blue eyes, and the unit will be so impressed by it, it'll say, well, this is surely a cat. But we kind of don't want that. We don't want crazy images. We want to somehow constrain this process so that it yields images that are like kind of sensible images. So we need some kind of regularizer that prevents crazy images from being produced. And a lot of the research on these kinds of visualization techniques actually deals with different ways to regularize images to prevent these kinds of really crazy solutions. A very simple choice that tends to work kind of okay is to simply regularize the sum of squared pixel activations. Essentially the squared norm regularizer that we saw before. And this makes a lot of sense because if we're at risk of generating a super cat with infinitely bright, infinitely blue eyes, well, that will have a very large norm, and this regularizer would be very unhappy with that. So this regularizer would prevent that solution. And there are some other solutions that it wouldn't prevent, but overall it's actually a sensible regularizer to use. Okay, so if we add this regularizer, and then we optimize, we might need to ask, well, which unit should we maximize? Like, what should S of x be? Let's start by choosing S of x to be a class label. So this will be a little more interpretable than saying, well, here's what we get at conv6, but we'll do the conv6 thing in a second as well. But for now, let's start with class labels. So that's like asking the network, well, what do you think is the image that maximizes the flamingo label, for instance? An important detail for getting this to work is instead of maximizing class probabilities, you actually want to maximize the activation right before the softmax. So what that means is the last layer, you have some linear layer at the end, and it's going to go into a softmax. You want to maximize this part, not this part. The reason for it is that in the softmax, you divide by the activations for all the other classes. And if you maximize that, Like let's say that your classes are flamingo, school bus, and hippopotamus. You want the image that is maximally flamingo, but what you're instead going to get is the image that's minimally school bus and hippopotamus. Right? Because you could increase the probability of flamingo by making it more flamingo-like or by making it less bus or hippo-like, because the probabilities are normalized. So actually, if you maximize the probabilities, you might get some pretty crazy stuff. You might get a crazy image that is extremely unlikely to be a hippo or a bus, and therefore more likely to be a flamingo. But if you maximize the stuff before the softmax, then you'll actually properly optimize for the thing that most resembles that particular class. So these are some results from this paper called Deep Insight Convolutional Networks, Visualizing Image Classification Models and Saliency Maps. Now, of course, these images are much less realistic because they're not starting from any real photograph. They're starting from some basically noise and then running this gradient descent procedure with this regularizer to produce the image that maximally activates that class in the network. But if you look closely at these pictures, you can see that there are some sensible things going on. So in the top left, you have a dumbbell. It definitely doesn't look like a dumbbell, but what it does look like is it looks like many copies of two blobby things with some kind of stick in between them. If you look at cup, top middle, definitely it doesn't look like a cup, but it has these kind of contours that look a little bit like one of these old style teacups. The Dalmatian definitely doesn't look like a Dalmatian, but there are definitely some spots in there. So clearly the thing this model looks for when it's trying to classify if something is a Dalmatian is just whether it has spots. If you look at the computer keyboard, third row, second column, there are some rectangular grids there that look a little bit like buttons, and the KitFox, third column, third row, definitely has some foxy ear-like shapes. The goose in the bottom left also clearly has some goosey contours to it, but again, it's very clearly not just a single goose. And this maybe gives us a little bit of insight for what these networks look for. For instance, it suggests that if a picture contains a goose, you were to take that goose and multiply it 20 times, it'll be more goose. So more goose is better. More goose is more goose-like. It also makes it a little bit apparent that this network is not so concerned with the particular contours of the shape. So as far as the network is concerned, a Dalmatian is really kind of a spotted blob. It's not about whether it has ears or eyes. It's really about the texture. Okay, so this can give us a little bit of insight into what the network might be good at and what it might be not so good at. Here are some visualizations from a different paper by Uzinski et al. Called Understanding Neural Networks Through Deep Visualization. It's a similar principle, but it uses a more nuanced regularizer. So the regularizer that they use is a little difficult to express as a function, but the procedure is as following. You update your image with a gradient, and then you actually blur the image a little bit. And intuitively what this does is it prevents the optimizer from producing really crazy high-frequency detail that basically fools the classifier. So the blurring kind of tends to make it a little bit, it tends to emphasize the importance of lower frequencies and therefore makes it come up with more coherent shapes. Then you zero out any pixel that has a small value, and this prevents little tiny minute noise from confusing the network. And then you repeat the process. So update with gradient, blur, push the really small activations down to 0, and repeat. And here's what they come up with for particular classes. And these visualizations now are starting to look a little bit more interpretable. So you can see the flamingo in the top left. The image actually has outlines of things that actually look like flamingos. So maybe for flamingos at least, this particular network does look for particular shapes. This heart beast, whatever that is, in the third column, first row, you can kind of guess from looking at this that it's some kind of animal with antlers, because while there are lots of complicated shapes in those pictures, one recurring theme seems to be this kind of deer-like head with big antlers. So whatever a heart beast is, I don't know what it is, but I'm going to guess it's some kind of animal with antlers. Billiard table definitely has some table-like flavor to it. And station wagon, if you look at it closely, you can almost see some windows and maybe an occasional wheel or two. Okay, so something sensible is going on. And Uzinski et al. Apply the same method to also analyze which patches maximally activate particular layers. So here they pick a class, and then they maximize the activation at a particular layer for that class. And you can see that at layer 8, For the pirate ship, for example, it tends to have a more holistic view. You can actually kind of tell that there's some sailing ship with masts, whereas at layer 7, it looks at kind of somewhat finer details. Similarly for Windsor tie, you can actually see some things that look a little bit like collars and ties at layer 8, whereas for layer 7, the shapes are a bit more abstract. And as we go to lower layers, things get obviously smaller because the receptive fields of those layers are smaller, and also a little bit more abstract, where when you get down to layer 4, it's really looking at basic geometric primitives like circles and swirly things rather than entire objects. And then if you get down to like layer 2 or layer 1, now you're just looking at edges and curves and things like that.